In this video, I want to go back to a question that I solved in previous video about the insect rotating on the record. In the other video, I was trying to solve this question using a method which was pretty dubious because I was trying to solve a rotational motion problem without using rotational motion. I want to show you in this video how, if you're willing to accept working with the angular variables, that this question is much easier. I would say it's easier. You might not think it's easier, but it's definitely cleaner and more elegant, and there's less kind of weird semi-unanswered questions about what's going to work and what's not going to work. So once again, the problem is we have an insect sitting on a record 5 centimeters away from the center of the record. The record starts to spin, so the insect starts to rotate. And how long will it take for the insect to make one rotation? I once again want to approach this using kinematic equations, but this time I want to approach it using angular kinematic equations. So my kinematic variables are going to be, I've got delta theta, omega initial, omega final, alpha, and t, of course, doesn't change because time doesn't care whether you're working in linear or angular variables. So let's try to think, which of the 5 variables here do I know based on the question, okay? So I've got, he starts to spin starting from rest. That has the same meaning in angular variables that it does in linear variables. Next up, the insect has a constant tangential acceleration, 0.5 meters per square second. That is not directly one of the kinematic variables, but it does tell me one of the kinematic variables because alpha, the angular acceleration, would be equal to AT over R using the relationships I described in a previous video. So that's going to be 0.5 meters per square second divided by 0.05 meters. And that gives me meters cancels out with meters. That gives me 10. And if you're following the units carefully, it's actually 10, and the unit is 1 over square seconds. But because we're working in radians, you can actually just toss a radian in there because radian is kind of a special unit that can kind of appear and disappear at will because it's not really a unit. It's kind of a natural quantity. Okay, so we've got alpha is 10 radians per square second. So let's put that over here. Alpha is 10. And what else? We want to make one complete rotation. A complete rotation corresponds to, remember we're working in radians, so a complete rotation corresponds to 2 pi, a rotation of 2 pi radians. So there's my 3 knowns, and my unknown is once again time. So now I pick my kinematic equation. I want the one that doesn't have final velocity in it. So the kinematic equation I pick is delta x equals VOT plus 1/2 AT squared. Now I change it to rotational variables, change the x to a theta, change the v to an omega, change the a to an alpha. And now I plug in delta theta is 2 pi. This is 0. I have 1/2 times 10 times t squared. So I'm going to have t equals 2 times pi times 2 over 10, and then square root that, and I get 1.12, which is the same answer I got in previous video. So that's really the proper way to solve this problem, is just to think in angular variables and solve it directly in angular variables.